Thank you very much, Mario. Yeah, so we can jump right into it. So there's a large variety of pathology that can affect the microstructure of human brain tissue. And I've listed a few examples of it here. So small vessel disease, tumors, edema, traumatic brain injury, different forms of dementias, and so on. And here I show a few different examples of how the microstructure changes for different grades of gliomas as compared to healthy brain tissue. However, these changes in the microstructure are often too subtle to be visibly seen with traditional imaging techniques. And also in other cases, such as in small vessel disease, the imaging markers that we do see are often show rather late disease progression. So instead, it is possible to look at tissue stiffness as a proxy for these changes in microstructure using a technique called magnetic resonance elastography, or MRE. And the way it works is that you throw someone in on a scanner and you vibrate the tissue of interest with a mechanical actuator where you produce steady state harmonic mechanical waves. And you can image these displacements using phase contrast techniques, and you'll obtain these 3D displacement maps. And then you can, through different forms of inversions, recover the mechanical properties of the tissue, depending on which model you choose to use. Now, this schematic here shows the technique being applied to the kidney, but it can in principle, of course, be applied to any tissue. And in my case, I'm interested in the brain. And we're quite lucky in that sense because the brain actually already vibrates. So with each cardiac pulse, your blood vessels swell and it will cause the brain to vibrate. And this is, of course, an exaggeration of that effect. It's way more subtle, but it is there enough to the point where you can image these displacements using still phase contrast techniques. In this case, the dense sequence at 7 Tesla. So I know Jaakko showed these figures before, but here you can see how the brain displaces over the cardiac cycle in the right, left, anterior, posterior, and feet-head direction. And you can see that it's really on the micrometer scale. And using this to then use the MRE technique is called intrinsic MRE. And an intuitive way to think about it is that the heart kind of pushes onto the tissue and the scanner feels the tissue pushing back on it. So it kind of becomes some sort of 3D palpation to the entire brain at once. And why are we interested in this? So there's a few advantages. And the first one is that we eliminate the problem of poor shear wave penetration through the skull. As you can imagine, the skull is more or less designed to stop any sort of extrinsic forces. And this is a problem we completely circumvent with this technique. Secondly, there's no need anymore for this cumbersome external actuation, which greatly increases the availability of the method. And then the third point is that we may provide some new insight into various brain properties. And the first thing I write here is that we might probe the natural stiffness of the brain. And what do I mean by that? So it's actually quite hard to try to measure brain stiffness because ex vivo attempts remove the brain from its natural vascularized state, which greatly affects the properties of the brain. And if we want to use standard elastography that I described before with the mechanical actuators, you actually stiffen the brain by quite large amounts. As you can see on this bottom graph here, you see how the stiffness increases with the actuation frequency. So again, you really change the properties of the brain by applying that technique. And that's also something we circumvent with intrinsic MRE. And we might also provide some poroelastic brain properties. So just as the stiffness is increased in the standard case with vibration frequency, you also diminish any porous effects of the brain. So you cannot use any poroelastic models to try to retrieve those properties, such as, for example, the hydraulic connectivity. So that's also something we're interested in. Now, of course, there comes some disadvantages with the technique. So you need sufficient precision in order to measure these subtle brain deformations, which is why we're interested in 7 Tesla imaging, as well as these more optimized sequences. And a problem that we run into is that fluid flows within the brain, such as from CSF motion or larger blood vessels, may introduce some artifacts that I'll show in a minute. So the aim of this project right here is threefold. So first, we just want to assess the feasibility of using this intrinsic MRE method using 7 Tesla and the DAN sequence. We want to assess the ability to detect regional variation in the resulting property maps, and finally to assess the repeatability. And I'll be quite brief on the method. So first, we want to of course measure these displacement deformations, but it was already done by Adams and colleagues in 2020, again using these parameters I've been talking about, and again I'm showing these displacements on the top right. And he measured 8 healthy subjects with repeated scans where the subjects were repositioned between the scans at a roughly 2 millimeter isotropic resolution. And then for the property estimation, we use a subzone based nonlinear inversion scheme, which uses finite element brane models. And the reconstruction itself is formulated as a constraint optimization task, where the goal is to minimize the difference between a computational model and this measured data that we have. And the computational model in this case is a heterogeneous viscoelastic material, as that is the standard that's being used in standard elastography. And I'm showing the governing equation here, where you can kind of see that we recover the complex shear modulus G star. And from this parameter, we can reconstruct our parameters of interest, which is the shear stiffness that describes how stiff the material is to shear stresses. And then we have the damping ratio, which is the ratio of viscosity to elasticity, which describes how quickly waves attenuate within the medium or the brane in this case. So then we can already take a look at some results. So these are the representative parameter maps of the shear stiffness and damping ratio. And on the right-hand side, you can see a T1 weighted scan just for anatomical reference. And you see we have both scans here where the second scan has been co-registered to the first scan. And what we can first do is we can compare these to the previous attempts at intrinsic MRE, which are a bit older now, you can't really see, but the first one is from 2012 and the other one is from 2015, where you can see we recover a lot more details, a lot more anatomical structure, which is really nice to see that the DAN sequence and the higher field strength really does a lot for the technique. We also see that particularly in the shear stiffness, so both these bottom ones are shear stiffness maps, so you can only compare to the left-hand side. We see that we see a lot of structure, but we see less structure in the damping ratio maps. It's more ambiguous and a little bit less symmetric. And you also see these bright valued areas here, these artifacts, which is what I referred to before as these fluid flow artifacts that arise. Yeah, we can carry on. So we performed this regional analysis. And in order to do that, we registered all the measurements to MNI space. And on the top, you can see a few slices of the template again for anatomical reference. And in the middle, we have the shear stiffness, and the bottom, the damping ratio maps, where we see the same patterns, that we have a lot of anatomical structure in the shear stiffness maps, and the damping ratio maps looks a bit more, significantly more messy. And we've defined regions of interest to take a look at these parameters, and we have the global brain, the white matter, subcortical gray matter, and the cortical gray matter. And here in these kind of larger regions of interest, we do see that most of our subjects, which each of these colors represents one subject, follow similar trends, which is nice to see. But if we zoom in a little bit, so with each of these regions, we have multiple subregions. So if we take a look at the subcortical gray matter, we get something that looks like this. And here we see the same as we saw in the parameter maps, that in the shear stiffness, we get really clear structure, while in the damping ratio, it's a lot more ambiguous. So our conclusion from, so this is just one of these subregions, and it's a lot bigger, this regional analysis, but I'm just showing this part for time reasons. But what we concluded is our method is indeed sensitive to enough to detect the regional variation, but the damping ratio maps exhibit considerably more inconsistent structure, which is likely due to data model mismatch of using a viscoelastic brain model at this lower actuation frequency of 1 Hertz. And so we performed this repeatability analysis. So here I'm showing Bland-Altman plots of our main regions of interest for the shear stiffness and damping ratio. And here the vertical dashed line is the mean over all measurements. The horizontal red line is the mean difference between all the measurements. And the upper and lower black lines are the upper and lower limits of agreements. And here we can see in general, we're quite centered close to 0. However, we do have one subject where which one of the measurements came out really, really bad. So with that really kind of shifts our means here, which is unfortunate, but still generally it looks quite good. And in order to compare to literature, I also computed a few more repeatability parameters. And here you can see that we fall quite nicely within the range of this standard technique, which I think is very interesting to see, because we actually don't even use an external actuator, which is the entire core of the standard technique. So here our conclusion is that our method shows comparable repeatability to standard MRE without using an external actuator. So to summarize these viscoelastic results, the shear stiffness map shows considerably increased level of detail compared to previous work. Our method is sensitive enough to detect regional variation. We see comparable repeatability to standard extrinsic MRE on a 3 Tesla system. And the main limitations right now are these fluid flow artifacts that we see. So these bright valued hotspots here, and data model mismatch of using a viscoelastic model at low actuation frequencies. Now, there is some previous work that has hinted that moving to a pore-elastic brain model may help alleviate this main limitation, and is something that I'm working on right now. So here I'm going to show you some preliminary results of this, in this case, pore viscoelastic reconstruction. So we successfully reconstructed these pore viscoelastic brain models or parameter maps. Here the parameters are a little bit different. So we have the storage modulus, which roughly corresponds to the stiffness, the loss modulus, which is the damping, and then this hydraulic conductivity parameter that I referred to before. And the thing I want to highlight here is that we see actually exactly what we wanted to see. We see a considerable decrease in these fluid flow artifacts. There is still one here, but these edge cases we can kind of deal with brain masking, and we still have one here. But in general, there is a considerable decrease in these artifacts. And as you also can see that in this damping parameter here shows a lot more symmetry and detail compared to in the viscoelastic case. So we also see less model data mismatch, at least for now. So to conclude, I'm going to repeat myself a little bit here, but we show that intrinsic MRE is feasible with 7 Tesla MR and the dense sequence. Our method shows comparable sensitivity and repeatability to standard MRE on a 3 Tesla system. The main limitations are artifacts introduced by fluid flow and data model mismatch by using this viscoelastic model. But moving to a pore-elastic model seems to really help us alleviate the main limitations, at least to a certain extent, and also provide some new insight into the mechanical properties of the brain. And that's all I wanted to share. So thank you for your attention.